Hello again, this is part 2 in a series, and it's going to be a continuation of the step file that we prepared of this mixing elbow, and we're going to talk about how to make sure that this is waterproof and exporting it as STL so that we can bring it into OpenFOAM. So in order to do that, you are going to need a software called Salome. There are other softwares, but I find this one to be one of the better ones, and this is Salome 9.8.0. And while it's booting up, I'm going to try to show you via Paint why it's important to waterproof the geometry. So let me get a pencil. So I'm going to try to draw the mixing elbow here. And remember that our mixing elbow has a volume. And what we're going to do here in Salome is surround this with a cube. So this cube will have volume. And that cube is broken up into smaller Rubik's cubes, even internally. So it kind of looks like a Rubik's cube. And we're going to have to determine, or OpenFOAM is going to have to determine, what's inside of this surface here. So inside the volume of the mixing elbow and what's outside. Because what it's going to do is it's going to find out which one of these cubes fall inside of this volume of the mixing elbow. And then it's going to cut away everything else that's from outside. And it can't distinguish between what's inside and outside without this surface being completely closed. And that's called waterproof. So we opened up Salome. It's just going to be blank at first. So you're going to want to go to Geometry, File, and import your step files. And that will be under Tutorial. Here you go. Okay. So it always starts out very zoomed out. If we zoom in, here you go. Here's what our geometry looks like. And it looks pretty good. And sometimes, I'll make these faces here inside of Salome, but I found it more convenient to do an on shape this time. So it looks good. To check if it's waterproof, the foolproof way to do it is selecting everything here and trying to make a solid out of it. If you can make a solid out of it, you're good. But we have a check type failed. And so we're going to try to figure out why that's happening. So we're going to go to inspection. And first we're going to want to check if there's any free boundaries, which I suspect is the problem. Yeah, we have a closed free boundary here, closed free boundary, and 3 closed free boundaries. Let's see what's going on. So you can actually apply and close and see. Oh, okay, so the problem is for the pipe wall, it has 3 free boundaries, and it's actually not the faces that's the problem. It's that these 3 items are actually not glued together, because we did export them as 3 separate files. So let's glue them together. And that in Salome I think is literally called gluing. Yeah, we can glue faces. So select the shape. Let's select multiple shapes, so all of them. And you can mess with the tolerances if that's an issue. And we're going to apply, close, and let's hide the rest here. So this is our glued volume. There you go. So everything is one piece together. So see, that's everything together. Can we make a solid out of it? I don't think so, because yes, unclosed shape. Okay, so we need to figure out what's going on. Free boundaries, no free boundaries, so that's not the problem. I think what the problem is that you can only make solids out of shells. So you see how there's different icons on the left of the name here. This one represents a shell. This one represents a compound. So this means that it's a mixture of a few different types. So we're going to need to make sure that this becomes a surface. So one thing that we could do is new entity, explode. So pretty much we can explode this shape into all of its subshapes. So notice how Salome understands that this is a different shape from this because there's a segment here. And if we explode it into its faces, now it's gonna hide automatically. Oh, sorry, never mind. There you go. It hid it, but then it represents each piece as a face. So like if we hide this face here, that's one whole face. Okay. And let's try merging these objects together, maybe, or fusing here. Maybe that's what I should have started with here in the beginning. So we fuse it. We can also decide to detect self-intersections, remove extra edges. These are things that might give us problems later, and something happened. We merged and it gave us problems. It seems like the bend here just disappeared, so let's go with, I think if we go back, oh, too far back. Unfortunately here in Salome you can't use Control Z, but they will show up in steps here on the left. If we merge if we fuse these together, maybe the issue is that it's removing extra edges. No, that wasn't the issue. So this actually ends up working out. It could have been that we're trying to fuse faces rather than surfaces. But there's a lot of tools that you can mess with. For example, sewing. So this one is very useful. I've used it a lot. Sewing, what it does is it'll find, I think, does it describe here? No. Well, you can go into the Salome documentation and it'll tell you how exactly it works. I think even how it works mathematically. But if I give you the synopsis here, sewing essentially will remove the little extra pieces sometimes that come out, little artifacts, if your geometry isn't right. But if you follow the geometry process making step by step in the previous video, then that usually isn't an issue. So we have a good surface here. Everything's one shape together. Let's hope that we can make a solid. Yes, we can make a solid. We made a solid out of it. So that means that this is good. So keep in mind it did just make a solid. So what I'm looking at here is not hollow. So make sure not to use this. But we're just using make solid to check that if it's waterproof, it's good. So we can delete that solid. So this fused one here, let's call it like geometry waterproof. And you can save that as a step if you want to, but I think we can go straight into meshing now. And let's make that all as one video, it's fine. So you click, oh, I forgot a step. So that bounding box, this box right here, we should be bringing that in. So the way we do that is we go to inspection, and we're going to go to center of mass. We're going to tell it to make a point, and it's called point 1, at the center of mass of this object. Okay, so made a point, there it is. And let's bring that back because I like to see it. So there it is. And then we're going to dimensions, bounding box. And it's going to create a box that completely encloses the geometry, but it's really close. In fact, they share a face. So we're going to want to scale it a little bit so that that's not happening, because OpenFOAM doesn't like it when your bounding box is too close to your surface. So let's apply and close, make this bounding box, but then you can choose this option here, scale transform, and choose this here, because this allows us to scale in each direction, X, Y, Z. Tell it, hey, make this bounding box, and let's just switch, call it the name. Let's call it, oh, it won't let me change the name. Maybe I can change it later. But let's make the central point the center of mass that we defined earlier, and then scale it the size of like 20% more, so 1.2 in each direction, and then close. So now it's got a little bit of overhang, and I believe you can make it a little bit transparent just so that you can see. Let's bring back the waterproof geometry. And yeah, there you go. It's not, now the edge is not too close, but is completely enclosed in this box. And so this one we can call rename bounding for our bounding box. Okay. Now we're ready to go into the meshing process. So let's start off by creating we're gonna try to make it look like the Rubik's Cube, like I mentioned. And that'll eventually be cut up in Snappy Hex Mesh, but to do that first, we need to create a mesh. So you can create a mesh of any of these objects, any of these geometries, but we're going to pick the bounding first, and you can choose many algorithms here. So if it's like a 3D shape, which in this case, we want to make sure we choose 3D because we want it to have an internal volume of those cubes. We want it to be cubes all the way through. We're going to, let's keep it as 3D. Later on, we'll use 2D for the surface, and then choose body fitting. So the body fitting one is good because we can actually mess with the parameters here and give it a resolution, if you think about it that way. So the smaller we make this f of t here, the more cubes that it will be broken up into. So maybe I'll give you a demonstration. So let's go with like 0.1 and apply. So after that, you don't have the mesh yet, so you have to actually compute the mesh. Here you go. And there you go. Here's our mesh. Let's, can we make a copy of this? Let's see. No, you can't Control C, Control V, but I'll just make a new mesh on top of this other one. And I just want to show you what happens if we change that parameter, that body fitting parameter. If we, for instance, change it to 0.05, and we're going to compare the two. Apply and close. Oh, I forgot to define the geometry. Let's define the geometry to be the bounding box. Compute it. And since this one is so much more higher resolution, it took a little bit longer, but that wasn't that long. And in the grand scheme of things, some can be take a lot longer. But you can see that it's broken up into more squares. But for this case, we don't need it to be that fine, just because this is an example. I'm going to go back to the original one, create that mesh again, and maybe we can compare the two. They look pretty similar, actually. Oh, yes, that's right, because what I did was I changed the hypothesis. Instead of making a new one, I edited the previous one. So yes, this one went back to 0.5. So let's make a new hypothesis. Create a new one, another one, and this one's called body fitting parameter 2. We're gonna make this one 0.1, 0.1, 0.1. Calculate again. There you go. Yes, so you can see the resolution is quite different versus this one. So we're going to stick with the lower resolution one just because it will make our computation a lot faster for the sake of this tutorial. Okay, so now that we've done that, we can hide this. And let's make a mesh of each of, no, not each of the pieces, the waterproof geometry. We actually should be making a geometry of each of these pieces, so I skipped a step. Let's go back. And we need to actually break up this waterproof geometry into groups because we need to export the STL files of the faces and the walls, these are called patches and walls, as different STL files. So we need to make separate meshes. So we're actually going to go to create new entity, group. You can create a group, and you can define what type of shape this group is made of. And we're going to choose faces because we want to make sure that these patches here are separate from the walls themselves. So let's do that. So select faces, select a face. You can add it to this group. So face number 2 has now been added to the group. And we should name this one. And so let's call this one, I think we called it inlet big before. Let's stick with that. There you go. Let's bring this back. Make another group. And in this case, we're going to call this one inlet small. And of course, we have to add it to the group. And lastly, new entity, group, create group, face, and just call this one outlet. Add it to the group. Oh, not lastly, because we actually need to separate the wall itself from the patches as well. So one more. Waterproof geometry, new entity, group, create group, face, and I believe, yes, this one is going to be comprised of multiple faces. So select this, hold down shift and left click to multi-select. So we clicked all 3 of these and we're missing this last smaller part. Add all 4 faces. We're not missing any. Good, we're not missing any. And call this one pipe wall. And so now we have it all grouped up, nicely grouped up. There you go. And they're shown here as like a subcategory of the geometry waterproofed. So go back to meshing. Okay, so there's going to be a little bit of jump cut because I want to go back and emphasize something that I didn't before. So after you finished grouping your geometry, and you can see the groups here, we go back to the meshing, and I'm going to delete these portions of the mesh because we're going to restart. And let's start by meshing the inlets. So you start by going to this right here, create a mesh, 2D, because we are working with a 2D face, which is one of the inlets. And you have a few different algorithm options here. You're going to want to go with either triangle, Mephisto, or NetGen 1D, 2D, and it would depend on your geometry, so try both and find out which one is better for your use case. But I would say usually you want to start out with NetGen 1D, 2D, and then you're going to, so you wouldn't have these here, it would just say default, because you'd have to create the parameters here at hypothesis, or maybe in the very beginning, if you don't know exactly what you want and you just want to have a first trial of meshing here, you can go to assign a set of automatic hypothesis, and you're going to want to pick triangulation and use the pre-estimated length. Okay, and apply and close. So of course this is going to create a new hypothesis, which is the NetGen parameters 3. So for you it would be called parameters 1, and then you can rename this to whatever you'd like. So apply and close, and so it doesn't pop up yet because we haven't computed the mesh, and to do that you press this cog here, compute, and this is what your triangulated surface would look like. And of course this is just the meshing for the big inlet, so let's just rename it big, and then let's do the same next for the pipe wall. It will be the same process, and we're going to go with NetGen 1D 2D because this is our first trial, and parameters 3. So you want to make sure that you choose the same hypothesis that you started out with. So once you pick one, you're going to stick with this all the way through. And so I'll show you why that's important. And that is because you can see here that the tips of the triangle here on the pipe wall, I'll just zoom out a little bit so you can get an idea of what the whole thing looks like. So this is the whole triangulated surface. and the vertex here of these triangles are going to match up. If they don't match up, which would happen if you didn't choose the same hypothesis, you would not have a waterproofed STL, and when you bring it to OpenFOAM, that might give you some unphysical simulation results. So it's very important that these match up. And of course, there's some different types of software within OpenFOAM that you can use to check to make sure everything is good. But I think it's best when working with CFD to make checks along the whole way. So every step of the way, if you make these checks, then your end result should be the best it could possibly be. So let's continue. 1D, 2D, parameter 3, because this is the one that we started out with, and we're going to stick with this same one throughout the whole way. Done. And these ones are fast because it's not a very big or complex triangulation. You can actually make the triangulation even more finer if you feel this is not sufficient. For example, these triangles are pretty big. Maybe they're, if this section of pipe is 3 meters, they might be maybe a few centimeters. And if you want to look at the flow within the millimeter scale, you can do this. So we're going to go back and delete this mesh, or we can actually clear the mesh data, edit the mesh, and then of course you'd have to start from the very beginning if you're going to do this, because you do have to stick with the same parameters all the way through. But if we check 1D, 2D, assign a set of automatic hypothesis, or just create one here, but I want to assign a set automatically, and then change this length here. So if we make this smaller, it was 0.8 before, let's go 0.08, so order of magnitude lower. Apply and close, and then compute that. This may take a little bit longer, but as you can see, the mesh is finer in comparison to the faces here. And of course, since we used a different set of hypotheses, you can see that this triangle's vertexes don't add up, and in fact you can see a gap here. That's a big issue when it comes to CFD. So this may or may not run in OpenFOAM, but when you look at your results, you might get something that doesn't make sense, and this would be why. But since this is our first meshing, we're going to go with the lower resolution one, and that should be fine. Once you move on to your mesh and time independence testing, then this is something that you're going to want to mess with. So we're going to edit, go back to parameter 3, which is the one that we're working with, compute that, and again, our triangles will match up. Great. These are still good. Now we're missing the outlet. I'm just going to go quickly now. And it looks like, yes, the triangles match up. That's great. So now you have your triangulated mesh, and you can export this into OpenFOAM. So the way we're going to do that is we're going to export as an STL file. It's going to give you this warning. That's okay. Geometries, and we were saving it under tutorial here, mesh, and then you will save all of them individually into this. And I have already saved them, so it's going to, of course, replace, override it, sure, doesn't matter. They're exactly the same. That's how I did it before. And then I'm going to go ahead and do the same, but I renamed these to all their relevant names. Okay. Okay, so now we're going to bring in the mesh for the background box, which I already did before last time, but I'm just going to show you again one more time. It was this one right here, this geometry, the bounding box. We're going to create a mesh. Again, what you do is you're going to go to 3D because you want a volume here. This is not a surface. This one is going to give you a volume, sort of like, think of a Rubik's Cube. You're going to choose body fitting, and we're going to choose body fitting here because it allows us to make the perfect Rubik's Cube type square, I think instead of going with the hypotheses here, I want to instead uh, go with the automatic hypotheses. Actually, I think I will show you, yeah, instead I will show you how to customize it. So here you can change the resolution, and I believe I already went over this. So smaller will be smaller, more cubes, and then a bigger number here will give you more cubes. We're going to stick with 0.05 and close. And hopefully this doesn't take too long. Okay, this is pretty fine for maybe a first one, but we're just going to roll with this for now. This was our bounding box. And when it comes to exporting this, you wouldn't want to export it as STL. You want to export it as a UNV file. So make sure you do that. And I do it in the same path folders where I keep the STLs. Anyways, once you've done that, you're ready to bring it into OpenFOAM and start the 3D meshing process using Snappy Hex Mesh. And so that'll be the next video. And thank you for watching.